Hi, my name is Nathan and this is a short intro to a pre-recorded lecture. The lecture was actually recorded a few weeks ago as part of a university or Discover University series and aired on Facebook. So you might hear me mention posting questions in comments, etc. But that isn't relevant in this stage. Now the lecture itself is on the research that myself and my group do here at Exeter, understanding or trying to understand the climates of planets we've discovered around distant stars or exoplanets. The lecture is about 37 minutes long. At the beginning of the lecture I actually said it would be about 15 to 25, but I lied. I overrun a bit. So about 37 minutes long, and at the end of it hopefully you'll have an understanding of the kind of science behind what we do here at Exeter. Now to go along with the pre-recorded lecture, there'll also be, or there is rather, a website that you can go to which has more resources, more videos, some explanation of some of the techniques in slightly more detail, and some exercises for you to go through as well, which would not only be very, very useful to you in understanding the kind of material that I'll go through in this next lecture, but also I think it'll be very useful for the project that I believe you've been set as part of the Scholars Programme. So I'd really urge you to go to that. You should find a link to that website in the material either through the Scholars page directly or on the main website hosting the pre-recorded lectures, etc. But do let us know if you can't find it. Now the other thing to go alongside with this pre-recorded lecture and the online exercises is a live Q&A session. Currently that's scheduled for the 27th July between 2:15 and 2:45, but I would urge you just to double check your schedules to make sure that time is still the same. And in that Q&A session, if you've obviously watched the pre-recorded lecture and had a go at some of the exercises beforehand, that would be great, and we can have a discussion, and I'm happy to answer any questions about the research or the work or the field in general, if you like. Now also alongside that, I grew up in Camborne, actually in the southwest, and have been at the university here in Exeter for many years, and I'm very, very happy and in fact keen to discuss the sort of journey through university and into an academic career. Talk about my own journey if it's useful, or answer questions and queries you might have on how you go about that and what it kind of looks and feels like as you progress through those things. Okay, great. So I hope you enjoy the lecture and the exercises as well on the online form. Get involved, get stuck in, and then I look forward to seeing you on the 27th of July and answering any questions you have. Okay, good luck. Hi, my name is Nathan Mayne. I'm a University of Exeter faculty member. I'm an associate professor in astrophysics and planetary climates. And I'm going to give you a short lecture today, about sort of 15-20 minutes, on some of the research that we do here at Exeter in my field, and also talk a little bit about, if you do choose to come to university, in particular Exeter, the kind of opportunities you might have. And if I have time at the end, I'll show you some of the projects that we're working on to engage with people before they come to university through some animations and game development. So you can post comments and questions throughout this next 20 minutes if you have any in the comment bar below this. I'll be there to answer them. I've pre-recorded this for two reasons. Number one, I was having difficulty making the live function work, so I wanted to make sure that the lecture would be sort of intact and ready, and secondly so that I can answer comments and questions as they come up. And if I can get the Facebook Live thing to work at the end of this lecture, I'll do a Q&A session where I can answer your questions directly. If I can't, I'll answer them in the comments to the best of my ability anyway. Okay, so I've got some slides which you'll see on the screen also, and really, as the title suggests of this session, I'm going to tell you about the sort of science fact search for life beyond Earth or aliens. And that's not really something which is solely in the realm of science fiction. In fact, perhaps in your lifetimes we might have the first evidence, if it exists, of life elsewhere. And a key part of that search, and something which is very close to my own research, is in order to achieve that goal, we really need to start to understand whether, or perhaps more accurately, the modelling of climates of all different sorts of planets. And that's grounded in our wonderful understanding of Earth that you can see here. So I'm going to walk you through some of the details. So we'll start off with a very general view of beautiful Earth, and talk a little bit about our sort of life on Earth and our kind of neighbouring planets. Now, Earth started 4,300 million years ago, formed from the material that was left over from when the sun formed, gradually sort of coalesced in a planet formation process. And we actually have images now. Stefan Krauss at University of Exeter and others have been able to image this process of the material that forms a disk around a star collapsing into planets. Now, we think that the first evidence of life in the rock record on Earth is from about sort of 3 billion years ago, so actually very early, relatively speaking, in the Earth's history. And that life has been able to maintain its position on Earth. In other words, Earth has sort of been conducive to life for that entire period, and evolution has slowly taken its meandering course to bring us to the present day. Now, of course, understanding what happens to our climate in the future is a really big question. It's one that I'm also trying to contribute to from a different perspective, actually, and understanding how anthropogenic climate change, as has been very much in evidence during the recent pandemic, where we've seen pollution and emission levels drop, we can see how plausible and possible that is. But understanding how that will change, and also on the longer timescale of as the sun evolves, gradually that body will expand and eventually it will actually sort of swallow up the Earth. But luckily that's not for about 9 billion years. But understanding that evolution of Earth is vital, because at the moment Earth is the only case of an inhabited planet we have. We need to understand how that works. Obviously, we also have 2 other planets in the solar system, which I've got images here. This is Mars and Venus, as it says. Now this is to scale. Now, those 2 planets are very similar to Earth. If you're an astronomer, they're roughly the same size. They kind of receive about the same budget of energy from the sun. But we know they're very, very different. Venus is extremely hot. It rains sulfuric acid. It's not a very nice place at all. Not conducive to life currently. But it isn't clear whether in the past Venus, at what stage rather, did Venus lose all of its water and become so hot. The reason it's so hot at the moment is simply because it has a really thick atmosphere, so it's wearing effectively a big puffy coat. Mars, on the other hand, in the current situation, is much too cold. Most of the water we think is frozen at the poles, and again that's effectively because it's wearing a thin coat. Its atmosphere is quite thin. But there are pieces of evidence which suggest that perhaps Mars had flowing water and might have been much more similar to Earth's kind of climate, at least, during a period called the Hesperian. We can see with the rovers on Mars, we can see the flow features on the surface, etc. Now, there are lots of other amazing planets out there, and even in our solar system, and I'd really urge you, this is a picture of the pole of Jupiter, I really urge you to check out the Juno mission that has a bespoke camera on it, specifically for the public, really, the wider public, to view that beautiful planet. And there's a huge amount of physics and interesting questions and puzzles around our neighbour giant planets, but I'm not going to talk too much about those today. So, really what I'm going to spend most of my time talking on is exoplanets, and these are planets discovered beyond our solar system. And really we take the context from Earth, Venus, Mars for the kind of planets that we think might be habitable, and trying to understand why Earth was habitable for so long, why Venus isn't. And then there are other forms of exoplanets which maybe are more similar to Jupiter. And then there are other forms of exoplanets we've discovered elsewhere which are nothing like any of those planets at all, and are in fact very, very different. So exoplanets themselves, the first one was discovered in the early 90s. Before that point, we didn't have any evidence of planets anywhere except in our own solar system. And then from that point now, we actually know that exoplanets are incredibly common. In fact, everywhere we think we might be able to find one, we have the sort of equipment that has the sensitivity, we do indeed find one. Now, the missions that have, or the facilities and the telescopes, etc., that have really contributed to finding these planets are many. There's the WASP mission, which is this one here. It's a lot of cameras in a shed in the Canary Islands. And then there are, of course, more exciting missions in the future, like this is an ELT. This is the European Extremely Large Telescope, and this is the James Webb Space Telescope. And these things will have the ability to really do far beyond what we can do today. But exoplanets themselves, how do we find them? Well, there are 2 main methods. The first one is called the radial velocity method. It's really simple. You can see a star in the center here and a planet orbiting around. And the planet has gravity too. And it's gradually wobbling, or slowly wobbling, the star. And you can see that this bottom line is showing the spectrum, or the light being emitted from the star. And it's being shifted by the wobble. And that's simply called the Doppler effect. It's the same thing that makes a police siren go up in pitch as you go as you go as it goes towards you, and down in pitch as it goes away. So that wobbling we can detect with the telescope, that wobbling of the star shifting the wavelength of the light. The second video I've got here is the other method. It's really simple. It's called the transit method. We'll start that video again. Simply you have a star, a planet moves in front, and the light gets blocked out. And you can imagine quite easily that the bigger this planet gets, the more light will be blocked out by this method. So quite a simple process to detect planets. Now the radial velocity one, this hidden planet has got a mass and a gravity and it's wobbling our star. And then the transit gives us an idea of what the radius of the planet is. So we have how much stuff, the mass, and how much is in how much space, the radius, and we can work out roughly what the density of these planets are. So very, very quickly, you've got something that's wobbling your star a lot, so its mass is high, but its transit, its block out of the starlight isn't as high as you might think. That could lead to it being a very massive, very dense planet, but quite small, maybe a rocky object. Something else, on the other hand, might have a much larger radius, and in that case we think it might be a puffy gas giant like a Jupiter or a Saturn or a Neptune. And that's great. These two methods I've got here, transit and radial velocity, both give us an idea of properties of the planet. They also tell us what the orbital period is, and that's how long it takes the planet to orbit, in other words, its year. And that's because the transit, as the light gets blocked, just happens once every one of the planet's years, so we can measure that. And the radial velocity wobble has a characteristic timescale of a year as well. But we can go beyond that. Now, the two things on the right I'm not going to mention too much about today. One of them is an image from what's called direct imaging. This is an image of a star in the centre here. This is about 1 million, in some cases could be as much as 1 billion times brighter than the planets orbiting it by using very sophisticated equipment. Sasha Hinckley at University of Exeter is really an expert in this. You can block out the centre light and actually detect the photons or the light coming directly from the planets. These planets are very young versions of Jupiter, similar to what Jupiter was like when it first formed, very hot, very bright. But in the future we hope to be able to push this technique to detect fainter and fainter planets. Microlensing is a technique to detect planets as well. It basically takes light from a very distant object and you observe it being bent by the gravitational field of the planet in between, the planet and the star. But I won't talk too much about that because it's more about detecting planets and not so much about the next step, which I'm an expert in, which is understanding their climates, or at least I enjoy looking at. Okay, so that's great. We can work out the mass and the radius, but we need to go further for someone like me to understand what these planets might actually be like. As I said, Venus, Mars, they're fairly similar to Earth, but if you actually land on their surface, we know they're very, very different. So we need a way to interrogate largely the atmosphere of those planets more deeply. So there are a couple of techniques. One on the left here is called transmission spectroscopy, and all that is looking at the size of this planet here as a function of wavelength. Now, as you look at some light, it might pass straight through the atmosphere, but perhaps not the bulk of the body. If you imagine the Earth's atmosphere, all of the starlight is blocked by the rocky part, the core, but some of the starlight filters through the atmosphere. We know that because it's daylight. So if we move to another part of the spectrum, it might be light that's blocked by the atmosphere. For example, UV light is blocked largely by the ozone in the Earth's atmosphere. So suddenly, we have the light from the star at transit on its way from me, the star, to you going through the atmosphere. You change the wavelength and now it gets blocked. And that tells us what's in the atmosphere. So we can build up a picture of the composition of these atmospheres. Also, that detects things like clouds. That's essentially composition too. Now, the other thing we can do is if we can get the light coming from the planet itself, various methods, one of them direct imaging, we can look at how bright the planet is at different wavelengths. So this is the different colours of light, different wavelengths here. These dots are observations from different telescopes at different wavelengths, and this is how bright the planet is basically. And these are models where we've tried to construct the atmosphere of that planet and try to see what it looks like and whether it fits these observations. And we'll talk about that in a little bit more detail later. But basically, understanding the brightness of the planet at different colours can tell you a bit about its atmosphere. We can go even further than that, and actually we can use something called a phase curve. So we can look at the brightness of a planet as it's orbiting around its star. So if you imagine this is the star, and this now is the planet, at this point, here you're seeing the dark side of the planet, and the day side of the planet facing the star is away from you. As I rotate around, or I orbit around, now you're seeing the day side of the planet and the night side is behind you. So by tracking that change in brightness that the planet is emitting from night to day side, as you can see in here, we can see a slight increase in the brightness. So this is where the planet goes in front of the star, blocks out some light. This is then as it's orbiting around and you're beginning to see the day side, and then this is the planet going behind the star. So from here to here. And that allows us to work out what the brightness of that atmosphere is around the planet. And here's an example from Heather Knutson. It's quite a few years ago now, actually, the first time I think this was done. And they've reconstructed here the brightness around the planet. Now, in the center of this line, that's where the planet is closest to the star. So you'd expect that to be the hottest and brightest, right? Well, actually, very quickly you can see this is offset, it's pushed to the side. And that was originally predicted actually by climate modelers, a man called Adam Showman, who's sadly passed away recently, but a real hero of the field. And that was a prediction that we'll talk about a little bit later. Now we can even go even further than that actually, and by looking at specific signatures in the atmosphere. I mentioned the radial velocity technique earlier, where my star is wobbling and I can detect the wobbles due to the Doppler effect, the wobbles, the motion of the star shifting the light. Well, I can use the same thing at really high accuracy. And this is an example here. These are lines, spectral features. These are emission from specific parts of the spectrum or specific wavelengths. And you can see that they've got this characteristic shape, and that's caused by the rotation of the planet. Now, these straight lines are just the ones in the Earth's atmosphere. That's actually coming from gases in the Earth's atmosphere. So you can see they don't move because the Earth isn't, at that time during these observations, isn't kind of moving around. So what we can do is get rid of all this stuff that is Earth-based, and then we can back out here what the orbital period, so how long it takes the planet to go around. We also have a way of knowing what the rotation rate is for these planets, because the ones we're looking at here are so close to their parent star that they're what's called tidally locked. It's like the moon and the Earth. They're locked together, so the same face always faces the star. Now what that means is that 1 year is 1 day. So rotating and orbiting at the same speed. So on this plot you can see on the screen, we can remove those out, and what we have is a leftover bit. So we can get rid of the motion from the year, the motion from the orbit, and we have a leftover bit. And that's actually used to calculate the wind speed in the atmosphere of these planets. It's been done a few times, led by Ignaz Snellen originally in Leiden. More recently it's been done by Tom Loudon, who was a master's student who worked at Exeter actually, and went on to do some work on this. And what you can do actually in some cases is, as the planet is coming in, just if you look at this slide here, as the planet is coming into the transit, you can detect the wind speed or the signature on this side, and then as it's coming out you can detect the signature on the other side, rather, other way around. So as it comes in you can see this bit, the light is coming through this part of the atmosphere, and as it's leaving you can come through here. So you not only can calculate the wind speed, you can calculate the wind speed in different hemispheres. So it's pretty surprising that I can tell you that we've been able to calculate the wind speed in 3 or 4 planets several light years from Earth. This is still very inexact at the moment. There's large uncertainties. The estimates are sort of 1 kilometre per second plus or minus half a kilometre per second, but with better instrumentation and better telescopes we'll gradually get better at that. Okay, now that's a whiz through the observations, and those are really important. They drive detection and characterization of exoplanets. But what I work on is modelling, and that's the field where me and my group try to contribute. So we try to take these observations, we try to understand what that means for the climates of these planets, and for that I link very closely to the Met Office. Now the UK Met Office, based in Exeter, are world leaders in understanding the climate and the weather on Earth, and indeed predicting the weather and climate. And of course the focus of the people working at the Met Office is very much that, it's very much Earth. But that model that they use is called the unified model. It solves the basic equations that could apply to any planet. So what I've done over the years is, with their permission, adapt that model so that we can use it for all these different planets. And that's really great because I can share information and expertise with the Met Office, and things that we're doing looking at exoplanets can also help as they start to understand our own changing climate as it kind of moves away from the present day situation as the climate changes. Okay, so what we've discovered really through this modelling and these observations is the first thing to take home, I suppose, from exoplanets is that it really is a zoo. There are so many different types of exoplanets out there, a staggering number really, and that's just in the 4,000 we've discovered so far. Now I'm going to show you, just for the rest of this talk, I'm going to show you a couple of clips from animations that we've made in collaboration with We the Curious and a visual effects company. They're a science exhibition centre in Bristol, and a visual effects company in Redruth, which was really a great experience working with a different kind of geek, someone that was into sort of programming and understanding visualizations, and they work with the gaming industry. And I'll talk more about that at the end. I'm also going to show you some real scientific output from some of these models. So let's first of all start with the basic different types of planets. The first ones we discovered were Jupiter-sized. They're very big, so they make their star wobble. And we found a lot of planets that were actually really close to their parent stars. They're called hot Jupiters, so they're like Jupiter and they're really hot. And they make their star wobble, and they also block out a lot of light, so they were easy to detect. Now you'll know already that actually there are nothing like hot Jupiters in our own solar system. All of the planets near the Sun are quite rocky, and all of the planets further away are the gas giant Jupiter-type planets. We also discovered, as I showed you earlier with direct imaging, we discovered this emission from young, bright Jupiters. I'm going to show you an animation to start with here, and this is of a particular hot Jupiter. This is called WASP 121b. This is an extremely hot planet, a few thousand degrees on the day side here, and you can see this planet is being absolutely blasted by its star, and it's forcing the atmosphere to evaporate. And we can actually see that in the observations that we make of this planet. We can detect this long kind of cometary tail here, which is being blasted away from the planet. Now we also think that this planet is so close to its parent star, the gravity of the star is actually sort of distorting this planet out of a sphere shape and into this kind of egg shape. It's actually the same thing that happens to Jupiter, but Jupiter is caused by the fact that it's spinning so fast, the middle starts to bulge. Even Earth bulges a little bit due to its rotation. Okay, so that's an example of a hot Jupiter, and that's one of the ones that I just want to focus on now to share with you some of the cutting edge science we're doing here. So what we use, as I mentioned earlier, is this Met Office global climate model, and I'm going to look at the screen here and show you some parts of it. The first thing is it's simply you set up a grid to capture your planet. So you build a grid that might represent the atmosphere, and then you calculate this thing called advection. Now that's just the winds. How do the winds move and respond to the pressures and the heating? You have something that calculates the chemistry. Now, of course, the chemistry on a really hot Jupiter-type planet is very different to the chemistry on Earth, but you can replace that chemical module with the chemistry relevant for hot Jupiters. And it turns out that a friend and colleague of mine, Eric Hebrard, noticed a few years ago that the temperatures and pressures of these hot Jupiters are very similar to the interior of car engines. So by working with the combustion industry, he was able to take some of that chemical knowledge from their experiments and feed it into our models. You can then deal with what's called the condensed phase, or clouds to you and I, and we go down, and the final step is this thing called radiative transfer, which is calculating the heating. There's another step where we also want to calculate what this might look through a telescope. So we calculate what the atmosphere might be like, and then we also calculate a simulated observation just so we can compare it with the real observations. But for the model itself, we go back round the loop and we move forward in time, calculating the winds, the pressure. Just like your forecast when you watch on the BBC News, for example, you'll see it steps forward in time and you're predicting where those different weather patterns might move, where the pressures are, where the different isobars are, for example. Okay, so let's give you some examples from this. Now, the first one up the top here is an example of just a pure plot of the temperature around this planet and the wind speeds. Now, you'll see straight away that this is kind of shifted. Now, here is this part here where I'm putting the cursor at 180 degrees. This is the longitude around the planet on the x-axis. This is the South Pole equator to North Pole. Now, here is where the closest part to the star is. Now, as I show you in the observations earlier, you'd expect this to be the hottest part, but it indeed is not. It's shifted. And that's because of the dynamics, the winds and the structure in the atmosphere. And this was first predicted, as I mentioned, with models before we observed this shift. So it was really great to see that you can take these Earth models of Earth's climate, same physics applies, but you change things like the chemistries and the temperature regimes, and you can actually predict what these planets are like and get it right. Now, the second thing we can do, beyond just looking at the flows in the atmosphere and the temperatures, you can see here this is sort of high temperature day side and cold night side. Something that was observed again by the pioneering Adam Showman was that you can get mixing between these cold and hot sides. So imagine you're a parcel of gas and you're on the hot side, you're blasted by the starlight, you're really, really hot, and that causes chemical changes in that piece of gas. Now that gas then goes to the night side and it's really, really cold. There's no starlight ever there, so it cools down rapidly. Now sometimes that process of shifting hot stuff to the cold area takes a while. It's faster than the chemistry itself to adjust. It's a bit like putting a snowball in the oven and then turning the oven up. The snowball obviously melts, but if you can keep putting snowballs in the oven, you can keep snow in the oven for a while. Okay, that's a silly example, but the point is you can move material between these hot and cold sides. So what you've got on this plot here is the same plot around the planet, South Pole, equator to North Pole. And this is an example, in this case, of something called methane. You all know methane, but methane and carbon monoxide exchange with each other. And if you get a certain temperature and pressure, you seal away that test tube, the balance between how much methane and how much CO you have will get to an equilibrium, a balance. And that's what's happening here. The balance is different on the day side as it is on the night side. One is hot, one is cold. But if we allow in our code to track the flow exchanging material between these two sides, then actually we see the structure completely changes. Now this is really important because when we look at the observations, what we might think we're seeing is light coming through this region here with a certain amount of methane. But actually we're showing if you don't understand the flows and how they interact with the chemistry, you get the wrong answer and your observations will look very different. You can see the methane concentration here is different to here. Now we can also look at clouds in the atmospheres. Now clouds on Earth of course are made of water vapour, ice crystal, graupel, all kinds of forms of water essentially. But on these planets in particular we have the type of materials made out of silicates and rocks essentially, and even sort of glasses. And what we've done is to couple a complex code that calculates the chemistry of these high temperature clouds, how they form and where they go, and we've run that with our model again like the chemistry, allowing it to flow. So you can see up here the different structures of different cloud species, magnesium silicate, and then we've got manganese sulfide up here. Now because this is okay, it might not be live but it's sort of one recording, I forgot to show you here. This was just a comparison with the observations and our modelling. And then this was just to show you that by looking at the chemistry here, we can link that to those observations I mentioned earlier, where you have, maybe you assume it's what's in equilibrium and balance, or maybe you assume it's actually allowed to move around. Okay, and let's move on then. So that's an example of these hot Jupiters. There are also young Jupiters. I haven't spoken much about those. But of course, our real interest is moving towards planets a bit more like Earth. There are these planets called super Earths, which are kind of in between Neptune and Earth. In the solar system, you get to Earth, and then there's a big jump to Neptune. But it turns out the most common sort of planet actually is right in that gap, which doesn't exist in the solar system, which is quite interesting. And we've also done studies of so-called lava planets, which is terrestrial planets, rocky planets. They're so close to their parent star that we think the whole surface is probably molten rock. So we're just going to show you an example of an Earth-like planet from an animation again. This is an example of a simulation again done with We the Curious and the team in Redruth from Engine House. And this, of course, for this planet, this is a very small planet in what's called the TRAPPIST system. And this is a small rocky planet that's believed it could possibly be habitable at some point. Now we know nothing about the surface here, so this is all speculation. But what we do know for this planet very much is about the star it's around. It's an ultra-cool dwarf, and a lot of the planets we're discovering that you might think are Earth-like, so they're about the same size as Earth, and they have about the same amount of energy from their star. They're actually being discovered around much smaller stars than the Sun. If you have a Sun and you have a planet blocking out some light, if your star is smaller, then you can probably pick up a smaller planet, because it blocks out a higher ratio of the light. So at the moment, these Earth-like planets are all orbiting these small stars. They're called M-dwarfs. They're much cooler than the Sun. That's why this looks redder in the sky. And also, they're much more active. They have these things called flares and coronal mass ejections. And basically, stellar activity is much more frequent. So one thing we're really battling with as a field is to understand if these planets are Earth-like at all. They receive a very different type of starlight. Now this planet has to get much closer to its star to stay warm because the star is smaller and cooler, and that's why the star looks bigger in the sky actually. And this is kind of calculated to be about what the star should look like. You can see all this auroral activity like the northern lights, and this is just speculation that you would get more of this due to this increased activity on the surface of this star. And here you can see one of the other TRAPPIST planets. Okay, so we've been working on understanding these different planets, and our group at Exeter is focused on trying to understand if we take a planet that has an atmosphere a bit like Earth, so a bit of water, some CO2 and nitrogen, then that's the planet we know that has life. We want to understand what happens to an atmosphere like that if it's orbiting one of these smaller, cooler stars. Now, the interesting thing about these planets is, as I mentioned, they have to get so close to their parent star to get warm that they end up tidally locked again, just like the hot Jupiters we were saying. So one day is permanent day, and one side is permanent night. So what that means is, on the day side here, shown in this plot, this is the day side of the planet, this is the night side, and this is height in the atmosphere. You have all the starlight is being received here, none on the night side. And that starlight goes to heating the surface, just like it does on Earth, lifting up the material, and this causes rain. Just like on Earth, you have belts around the equator where the sunlight reaches the surface, heats up the air rises, and as it rises it cools and it rains, and that's why there's belts of rainforests. Then that material moves away from those regions and sinks, but it's dry. So that's why there are belts of desert. So if you look at a globe, you can see belts of rainforest and desert. And actually, how far that material moves between the equator and the pole is controlled by how fast the Earth is rotating. If you imagine here's the Earth, I'm at the equator and I'm rotating around the atmosphere once per day. And then I try to move here, well, I'm getting closer to that rotation axis. So just like trying to sit on a roundabout and get to the center, I experience a force as I move around. It's called the Coriolis force, and that means that if I'm rotating very fast, I get sort of sheared off. So if you look at Jupiter, it has lots of jets because it's rotating very fast. Material tries to move towards the pole and it gets sheared off. On Earth, that can allow material to cycle sort of up to about the mid-latitudes and just between the sort of belt of deserts and tropical rainforests. Now, on these tidally locked planets, it's very, very different, of course. Effectively, you have this entire day side with the whole day side lifting up and raining everywhere on the day side should water be present, and then materials circulating around to the night side. And what we've done is to do simulations. I won't talk you through the detail of these, but these are just simulations of these planets where we've tried to predict what this might look like. So you can see here, this is the whole planet, and this is effectively the cloud cover, and you can see over the hotspot there's this cloud cover, and we can zoom in and run high resolution simulations of this huge region of convection, uplift of clouds and rain. Okay, so that's some of the modelling work that we've been doing, trying to understand the climates of these distant planets and try to determine ultimately if they could host life. And that's all done at Exeter, and the idea here is to generate this kind of ability both in software like big models, but also people and expertise to try to understand planets across a huge range that they exist, everything from lava planets to Jupiter type planets to hot Jupiters and the other ones that I've mentioned today. And that really is work that relies on the Met Office software that we're able to use. And as I've shown you a couple of visualizations, we also have produced those to enable us as well as people in the wider public to start to understand the kind of things we can study and the kind of things we can work on. So just to leave you, it's an old plot actually, it's about 9 years old, but I like it because it shows a good point. This is the sun in the center. This is a ring at 10 light years, 100 light years, 1,000 light years, and 10,000 light years from Earth. And all of these dots are stars around which a planet has been detected. And this is back in 2011, so there's many more dots now. But the point here is that there are exoplanets everywhere. Indeed, as I said, everywhere we think we look and we are able to detect one, we have the techniques to detect one, we indeed find a planet. So currently there's over 4,000 exoplanets been discovered. Now, if you think about trying to estimate the number of potential Earth planets in the galaxy, to start with, there are about 10 to 20% of the planets that we discover are probably or 10 to 20% rather, of the stars that are like the Sun probably have a planet like the Earth orbiting them. How do we know that? Well, we look at all the stars that we've detected planets around, and we work out how frequent planets are from those kind of statistics, and we can project that on. Now I stuffed that up a little bit, so let me repeat it. So we think that about 10 to 20% of stars like the Sun probably have a planet like Earth orbiting them. Now I don't mean like Earth, I mean Earth-like, in that it has about the same size and about the same amount of energy. We're not sure if they have trees and universities and things like that. We don't know that yet. Now what that means is that in our galaxy we have about 300 billion stars. Of those, about 20% are like the Sun, roughly speaking. And we've just said that our statistics show that of those suns, about 10 to 20% of those sun-like stars, about 10 to 20% probably have an Earth-sized planet with about the same amount of energy being received as Earth. That leads us to 6 billion planets that could potentially be Earth-like in our own galaxy. That's a huge number. Now, if you look out of the night sky, our galaxy is like two fried eggs back to back. There's a big bulge in the middle, and we live out in this kind of white area, in the white. And as you look along, you see the bulge. That's called the Milky Way, where all the stars are. Now, the Hubble Space Telescope looked away from the bulge into the dark of the deep sort of universe, if you like, and it stared and stared and stared, and it produced this image called the Hubble Ultra Deep Field. It's about the size of the moon, and actually in here there are 10,000 galaxies. Now, they're not all like the Milky Way, our own galaxy, but roughly, if you think about next time you're out in the dark, how many times you can sort of fit the moon across the night sky, times that by 10,000, and then each one of those could have as many as 6 billion Earth-like planets. It shows you that the number of potentially Earth-like planets in our universe is huge. But of course, at the moment, we only have evidence for life on Earth itself. So that means it's sort of we need to look after it a little bit more and make sure that it survives on this planet. Okay, so that's the end of our kind of formal lecture on the science and the research, but I just wanted to take a few moments to show you. Now, I'm just going to show you a very short clip from the movie that you saw some clips from.
Trading is not for everyone, but if you are a trader.
Lovely adverts. So on here, this is available online, and you can find this quite easily. Maybe I'll post the link in the comments section. And this is the video that we made with Really Curious, where we explored these different planets, and we're able to show you all sorts of things. Like, for example, this is an artist's sort of visualization of what it's like to be actually in the atmosphere of one of these hot Jupiters. And more recently, we also did another one of these animations, but this time we did it in a much more sort of cinematic sense, to try to give you a feel for what it might be like in the future to explore these planets. And I'll post this link in the comments as well. But you can see, for example, here we've imagined what it might be like to be dashing across the surface of one of these planets, or indeed later even on a sort of research base. It's just a bit of fun, really. Okay, so I'll post those in the comments section if you're interested. And the very final thing is we're currently using all of this sort of information to create a game in partnership with some students from local schools to try to, not just to make a game, but also to try to connect these techniques and these visualization techniques that we've made and the techniques that we use in real science to try to make those accessible to people and show that they're conceptually not that difficult. So this game here will be up and running soon, and you'll be able to have a go, but it's not ready just yet. Okie dokie. Thanks so much for your time, and we'll stop there.